In this video, we will show how to analyze, within a single simulation and without any Java macro, the behavior of a boat over a whole range of velocities, actually implementing a parametric analysis. Suppose to have already set up a sink and trim simulation for the boat that we see here, having applied the 6 degrees of freedom model to let the boat freely move on the z direction and rotate around the y-axis. In order for this method to work, it is necessary to arrange the simulation using a moving reference frame instead of setting the velocity of the wind and current under the VOF wave model. This means that under the physics model VOF waves, both the current and wind velocities are set to 0, as we see here. The velocity is instead imposed on a moving reference frame, which is assigned to the whole region under the motion specification node. Here it is called MRF boat, and it is set as a rotation and translation moving reference frame, set to reproduce an X translation of 2 meters per second. For the sake of this demonstration case, we can see that the sinkage and trim monitors get almost converged in 10 seconds, which in this case corresponds to a total of 10,000 iterations. Now, the key for the effective setup of the parametric analysis is the definition of a function for the velocity that changes its value each 10,000 iterations, which we will see is quite simple to achieve through an user-defined fill function. So, let's first of all define a new function, which we call I, giving to him the same function name I, and with the definition involving the function floor, which is the integral part of the division among iteration -1 and 10,000. This means that this function will have a value 0 for the first 10,000 iterations, then switches to 1, 2, 3, and so on. Now, it is straightforward to define a new function val, giving again the same name, val, and with definition 2.0 plus 0.5 multiplied by the function I. In this way, we will investigate increments of the velocity of 0.5 meter per second each time. So, let's then go to the moving reference frame and set the x component of the translation velocity to the function created val. Now, to study the range of velocities from 2 to 4 with step 0.5, it is sufficient to set a total number of iterations of 50,000, namely a maximum physical time of 50 seconds. So we have arranged a simulation that spans a certain range of velocities. And now we can also easily set up the post-processing in order to effectively see the results. First of all, we define a report to get the information of the imposed velocity, recalling the field function val. So we select on the scalar field function the user-defined field function val, and for the parts all the regions. Okay, now for the velocity, sinkage and trim, we create another set of monitors and plots, with the clever trick to set their frequency update exactly each 10,000 iterations. So we select the monitors, we go to their frequency property, and we set 10,000. In order to distinguish these plots from the previous ones, which we keep for debug reasons, we called the ladder global, since here we will see the information associated with the global parametric run. and the same we do for the names of the plot. As a final useful thing, we can set the autosave properties of the simulation, thus enabling a saving with frequency 10,000 iterations of exactly 5 files, in order to get automatically saved in different files the final configurations for each velocity. And now we are ready to clear and launch the parametric run. Okay, and so let's open directly the simulation with the final results. And on the plot we have the values of the sinkage and trim for the different velocities as different points in the plot, from which we can clearly get the general trends. We can also look at the original plots as functions of time, as a sort of convergence check, controlling that for each velocity convergence is reached. To see the quantities as functions of the velocity, we can proceed in this way. Select all the global monitors and create a new plot, single plot. Then select that plot and export it on a CSV file called all. And then immediately re-import it back in StarCCM Plus as a table, with a new table file, and calling the file all.csv. With this table you can easily create an XY plot with, in the tabular tab, the X column is the velocity and the Y column is the sinkage. Now we can adjust some graphics properties, making a line and bigger dots, in order to directly get the final curves of the sinkage and trim as functions of the velocity, obtaining the final result of our parametric run.